Welcome back! This lecture continues on the theme of the previous one. Last time, we defined order completeness in terms of cuts and proved that order complete sets have the least upper bound property. That was all very abstract. Today, we make things a bit more concrete and return to our discussion of Q versus R. Specifically, we will focus on the fact that Q is not order complete, while R is. You may ask, what's the point? We already know that Q has holes. Numbers like square root of 2 or pi are not included in the rationals. The first reason is that the set of rationals have both an algebraic structure and an order structure. On the algebra side, it is a field, which we recall just means that we can do the usual arithmetic operations of addition, subtraction, multiplication, and division on its elements. Numbers like the square root of 2 are known to be missing from the algebraic side. For analysis, it is convenient to be able to know that there are no further missing numbers that comes from the order side of things. Both the algebra and order structures for numbers are important for analysis. A second reason is that some irrationals are more justified to be included than others. Numbers that look like repeated applications or radicals. Here I give the example of square root of 2 or the cube root of the quantity 2 plus the square root of 15 can be expressed as roots of polynomials. The case of including such numbers among the real numbers is strong from the algebra point of view. Numbers like pi and e, however, cannot be written as the root of a polynomial with rational coefficients, so the algebra case for their inclusion is a bit weaker. However, from the order point of view, there's little distinction between the two classes, and this gives a pretty fair way of asserting the need to include all irrational numbers in the reals. With the motivation out of the way, we next show that the rational numbers is not order complete. To do so, we just need to find a cut such that neither SU and SL have their endpoints. Notice that to show that Q is not order complete, we just need to provide one example. We will not attempt to list all possible such cuts. We define SL as a set of all negative rational numbers together with all rational numbers whose square is less than 2. We define SU as a set of all positive rational numbers whose square is larger than 2. The conditions used to define these two sets are almost negations of each other. Were they negations, then automatically between SL and SU, we capture all the rational numbers. The only possible missing number that makes the two conditions not direct negations is the positive solution to Q squared equals 2. But we know that this number would be square root of 2 and is not rational. And so we see that the two sets cover all possible numbers. To show that SU and SL make a cut, we need to show that elements of SL are always below the elements of SU. We argue by cases, since an element of SL is either non-positive or positive and squares to less than 2. In the first case, as all elements of SU are positive, we see that the Q from SL must be below any element from SU. In the second case, since elements P in SU square to something greater than 2, we see that P squared is bigger than Q squared. Since both P and Q are positive, we must have P is bigger than Q. Having verified that SU and SL make a cut, we next show that SU has no minimum and SL has no maximum. These together show that Q is not order complete. Next, we prove that SU has no minimum. The argument is a bit long and technical, so bear with me. To prove that SU has no minimum, we need to show that given any Q, in SU, we can find another P in SU that is smaller. To do so, we first notice that Q in SU implies that Q over 2 minus Q inverse is positive. This follows as Q is positive and Q squared is at least 2. Since this quantity is a positive rational number, we can apply the Archimedean property of rationals to find a natural number n so that 1 over n is less than Q over 2 minus 1 over Q. Doing some algebraic manipulations, we find that Q squared minus 2Q over n is still bigger than 2 for the n that we chose. This can be rearranged further to read that the quantity of Q minus 1 over n squared is also bigger than 2. On the other hand, since 1 over n is bigger than Q halves, it is also no bigger than Q. So setting P being Q minus 1 over n, we find a number that is positive, whose square is at least 2, and so P is in SU. But 1 over n is positive, so P is less than Q. And this is what we want to prove. Notice that here the Archimedean property played an important role. To complete the proof, we need to show that SL has no maximum. As before, there are two cases for SL, since elements of SL are either non-positive or positive and squares to something less than 2. In the first case, if Q is a non-positive element, since the positive number 1 is an element of SL, we see that Q cannot be a maximum. In the second case, given a positive element of SL, we find that the condition Q squared is less than 2 can be rewritten as 1 over Q minus Q over 2 being positive. By the Archimedean property, we find a natural number n such that 1 over n is half that value. Using the Archimedean property again, we can choose n possibly by making it bigger so that 1 over n squared is less than 1 minus Q squared over 2. The latter is positive since Q squared is less than 2. Doing a bit of arithmetic, we see that the two conditions on 1 over n and 1 over n squared can be combined using that Q is positive to read Q plus 1 over n quantity squared is less than 2. So the rational number P equaling P plus 1 over n, Q plus 1 over n, is an element of SL and bigger than Q, and hence Q is not a maximum. The proof of this last result, that the rationals Q is not order complete, is quite technical with all the details filled in, relying heavily on manipulating inequalities. I encourage you to rewind and watch through the proof a few more times to make sure you understand what is going on. While the exercises and the homeworks you will be assigned will not be this involved, in a course in analysis, you should expect plenty of manipulations of inequalities throughout your work. Make sure you are comfortable manipulating inequalities between variables that can stand for real numbers. Coming back to the proof, you should find that at a conceptual level, the proof is not too bad. In order to show that Q is not order complete, we need to find a cut of Q such that neither half contain the endpoint. And so, we need to first check that we are making a cut, that the two sets can be joined together to give all of Q, and that one set contains elements that are bigger than those of the other. Next, we need to show both that SU contains no minimum and SL contains no maximum. It is in this last part the proof got technical. The essence of the proof, however, is simply that given an element Q in a relevant set SU or SL, we need to find a way to construct a new element P in the same set that is smaller or larger than Q, as the case calls for. The technical parts are how we implement this precisely to find the element P, by using the Archimedean property. And now, we finally turn to the main character of our story, the real numbers. For our purposes, the only properties that we will be needing concerning the real numbers are: first, you can perform the usual arithmetic with them. Second, given any two real numbers, they can always be compared. And finally, to distinguish it from the rationals for which the first two properties also hold, the real number line is order complete. This is our first main takeaway fact from this course, that the rational and the reals are alike in many different ways, but the main analytic difference is that the rationals are not order complete while the reals are. In fact, the reals can be thought of as obtained by filling in the holes left behind by the rationals. Imagine trying to perform different types of cuts on the rationals. Sometimes you will cut exactly along a rational number, and the two sets SU and SL will have one that contains the rational number in question, and that number will serve as the endpoint. Sometimes you will, however, cut not along a rational number, and the two sets SU and SL will be both without endpoints. If you manually add a point to the line to fill in that hole, and do this for every hole you can find among the rationals, then you will get back the real numbers. This procedure is called the Dedekind cut and is described on pages 30 and 31 of your textbook. We will not cover it in this course. We will pause here for this lecture. In the next and final lecture of this week, we take a look at some of the basic properties of the real numbers, starting just from these properties. See you next time.